Are you watching this? Water. Pure water. Hello, and welcome back to Shady Sundays. This time, on Tuesday. So today, playing off of last week, we're going to be making some water. This topic kinda dives deeper into mathematics, but you're a smart one and you'll manage. I believe in you. I'm sure you've seen a lot of water throughout your life, but one rarely stops to think what actually happens during the act of seeing water. Well, water, just like air, is a fluid. And the more fluid you have to look through, the less you see. Meaning, depending on the observer's point of view, water will look different. This of course happens automatically in nature because we are living in a simulation. To kick things off, a quick recap from last episode. So, you compute the NDC, then multiply it by the inverse projection matrix so you can go from clip space to view space, and now you have the view vector. So, what was the view vector? That's right, it's the direction we are looking at times the view length. Now, using the view vector, we need to compute the intersection point. Luckily, Godot has a built-in way to do that, so we just do it. Now, for the actual water effect, there are two things we need: the distance to the land and the distance to the ocean. From last episode, we already know how to compute the distance to the land. Just get the z-axis of the view vector and multiply by -1. Okay, so half the work is done. Just hold on a little longer and we'll have some water. Now, the second thing on the list, the distance to the ocean. What ocean? There is no ocean. And that's the hard part. We need to compute the distance to a non-existing ocean. Now, to compute the distance to the ocean, we need an intersection function. And since the ocean can be defined as a plane, we're going to be using a plane intersection function. So, how do we do that? Join me into my notebook so we can explore that. I couldn't find my notebook, so we're going to be using Krita. First, let's start with our ocean. As we discussed, our ocean will be a plane, and how do we define a plane? It's simple really, we need two things. The plane's normal, which will be this vector right here, and the plane height, or the distance we need to travel along that normal to reach the plane. For the sake of simplicity, in this demonstration, the height of the plane will be 1, and the normal will be up or 0, 1. Okay, so now let's continue with the observer. And on the behalf of the observer, we need two things. We need its position. So for the sake of the demonstration again, this position will be 0, 3. And also we need the view direction, or the vector the observer is looking at. This vector will be 1 minus 1, but to be a direction, it should be normalized. So it will turn from 1 minus 1 to, it will turn to square root of 2 over 2 minus square root of 2 over 2. These are the four things we need to compute the distance to that ocean. And let's start with that. Let's compute it actually for this example. The first thing we need is minus the dot product of the camera position and the plane is normal. So that will be 0, 3. Then we need to add the height. And then we need to divide this whole thing by the dot product of the view direction and the plane is normal. I'm just going to write there because this whole thing is too long. After computing the dot product, we reach, and after further simplification, reach 2 times the square root of 2. By the way, there will be an article full of different intersection functions on the Git page. Just saying. First, let's see the fruits of our labor in 3 dimensions. Kinda boring, but it's accurate. Now that we have the 2 parts of our equation, let the great subtraction commence! Oh fuck! Okay, there we go. I'm sure my shitty editing and my shittier acting stood in the way of information, so let's try and explain what just happened. Okay, so let's see why there's this sky ocean. Okay, let's take a closer look at a case where our observer is looking at the sky. Then our intersection function will return a negative value, which mathematically makes perfect sense, but in our case, we aren't a negative distance away from the sky, we're an infinite distance away from the sky, meaning that if we see a negative value, we just replace it with an arbitrarily large one. And now, the other problematic case, which is when the observer is submerged in the ocean. In this case, our intersection function will return the distance to the ocean surface, but in our case, we don't need to do that. We can assume that we are submerged under the ocean if our current y value is lower than the sea level. And if that's the case, we can just return 0. We didn't go through that much trouble just to get a plain old blue color, did we? So let's fix that. First, defining some parameters. Let's define the ocean color, the deep ocean color, the sea level, and the ocean depth. So, with all those 4 parameters, it's rather natural just to mix the ocean color and the deep ocean color. But we need a factor to do it. So let's compute that, and we have a beautiful ocean. You're still not satisfied, huh? Okay, we'll make it shine. Just define the color, strength, and smoothness of the specular highlight, also the direction of the sun, get those vectors, dot them, compute the exponent, square that bitch, add it to the albedo, and then congratulations, you have made it worse. A wise man once said, "Ocean with no waves is nothing more than a waveless ocean." Okay, so we need noise. You know how that goes. Just get it from the internet, because it's a humongous topic on its own. This time, I would recommend get something that is non-periodic, because if you do, your waves will look like that. Now, we have the noise, now we need some parameters, we need to compute the ocean normal, and then calculate the specular highlight with that new normal. Beautiful, right? Wrong! Hot time to taste. And now, finally, it is done. Thanks for watching if you're still watching. I really do appreciate that. And it would, again, really mean a lot to me if you subscribe. Also, bye. A wise man once said, "Ocean without waves is nothing more than a waveless ocean."